So we need the...
You need that Pauling scale, and it's probably on your...
It's on our notes, but it's too hard to read.
Okay, it's also in the color page that I gave you too. If I think about it, I'll get you a bigger one of that printed out. Yeah. All right, so find the electronegativity difference between each of the three bonds, then put them in order from most polar to least polar.
So if the number's bigger, it's going to be more polar?
Correct.
Sweet.
The difference between them is bigger.
And you're never going to have a negative number.
Yeah, it's not going to be negative because you're always going to take bigger minus smaller.
Need it easier with...
Is that the order you had them in?
Yeah.
Good. Did all of them fall into the polar covalent range? Were any of them close enough to be nonpolar?
The
No.
OF was somewhat close.
But it was still considered
was
polar covalent.
still-
Okay, so when it becomes polar covalent, what does it form in that bond? Do you remember we talked about it? If it falls in...
A charge?
Okay, but it's not a full charge, it's a
Partial.
partial, right? Partial positive, partial negative will start to form when we see those polar covalent bonds. All right, good. I don't think we need to do another one. Which of the following bonds would be the least polar, yet still be considered polar covalent? So still we're looking at subtracting your electronegativity differences. I don't think we need to go over this one. Is that fine?
Yeah.
Okay, great. What happens when we have O bonded with O here? Yeah, you're going to have an electronegativity difference of 0, which would be the most pure non-polar covalent bond. Oops, I can't spell. Non-polar covalent bond, right? If you've got two elements of the same. All right. Most polar without being considered ionic, we can look at that, but I think we'll be fine with that, right? Most polar without being considered ionic would be the biggest difference in polarity without going over to 1.7, right? Going over 1.7. Magnesium and oxide would go over 1.7. How could I know that just based on looking at it?
It's a metal and a non-metal.
Perfect. It's a metal and a non-metal. Good. These are non-metals. Why is silicon different here? It's not a metal or a non-metal, it's a metalloid, right? So it'll be the most kind of in the middle there. All right, good. So we don't have to do the math to look at those, but we could have if we really wanted to. All right. So if a molecule is polar enough, or if it has a charge distribution that is polar enough, it gets what's called a dipole moment, which sounds more dramatic than it actually is. Okay? If we have a region of positive charge and a region of negative charge, that's what we consider a polar molecule. Okay? We use an arrow to represent the dipole moment. The arrow points toward the electrons. So it points toward the negative region, right? It's pointing, it's like you're asking, where are the electrons, right? And you just draw the arrow that points to the region that has more electrons. Okay, so I'm going to show you kind of what that looks like here in just a second. But dipole moments are generally drawn with an arrow. And then I even put a little plus sign on the positive side of the dipole moment, right? You can kind of cross the tail of that arrow and it'll tell you again that that's the positive region. Okay. So let's look at it with water here. We've got water on your next slide. If I look at the Lewis structure for water, okay, and I'll just draw the Lewis structure in the same orientation that they have it. Right? Do you remember doing Lewis structures in Chem 1? A little bit. Okay, we're going to get back to them eventually. But if I look at the Lewis structure for these, I'm going to look at the individual bonds between hydrogen and oxygen. And I know that oxygen is more electronegative, right? Go ahead and look at the values between hydrogen and oxygen. Is it going to be a big enough difference to be considered a polar covalent bond
No.
between hydrogen and oxygen?
Oh wait.
What's the difference? Is it more than 0.4?
Yeah.
Right. So now we're going to have a polar covalent bond take place in each of those bonds, right? Each of the bonds that connects hydrogen with the oxygen are going to be considered a polar covalent bond. So we can draw little mini dipole moments that tells us the electrons in that bond are being drawn toward oxygen. And so now we see this region in our molecule that has heavy location of electrons. And so that's what this full dipole moment is for, right? Like that. Uh-huh.
So the element with the higher electron negativity is always going to be the one on the positive.
On the negative, on the front of the arrow, right? We're pointing toward where the electrons are going. And oxygen's pulling on the electrons, so that's where our arrow goes. It points toward the more negative, right? Okay, so now these two little mini dipole moment arrows, right, within the bonds, point us to a region of electrons. And so the dipole moment for water looks just like the one drawn here or the one drawn here, right? When we look at the dipole moment for a whole entire molecule, not just the individual bonds, we're looking at where are the lone pairs? Where are the electrons located? Right? Because three-dimensional shape dictates that the electrons are arranged in a certain way, and we'll kind of get into that in a little bit. But this heavy, like red region is where all the electrons are located. Because not only is there lone pairs there, let me draw, right? Not only do we have lone pairs here on oxygen, but we've also got the electrons from the bonds being pulled closer to oxygen. So we see a big dipole moment heading in that direction. Does that kind of make sense? All right, what questions do we have about that? The reason it's drawn in this particular shape has to do with its three-dimensional molecular geometry, right? If I was going to draw just the Lewis structure for water, I could have drawn it like this. And it wouldn't really have looked like there was any certain region of electrons that was more, concentrated than another. But we have to draw it with its correct three-dimensional shape because that'll tell us if there is truly a region that's more negative than others. Okay? Here's what happens if we have dipoles that cancel, right? If we have polar bonds but a non-polar molecule, this is kind of an example of what that looks like. Okay, so tell me the difference in electronegativity between carbon and oxygen. What's the difference in electronegativity between carbon and oxygen?
More than 4.
Is it more than 0.4?
Yes.
Okay, so that means we've got polar bonds happening here. There's a polar bond. And which one is more negative, carbon or oxygen?
Carbon. Oxygen.
Sorry, more electronegative would be oxygen, right? So here's our dipoles within the bonds, but they cancel each other out, right? They're pulling on that carbon with equal force, so they cancel out, and this results in a non-polar molecule, right? So this would be a non-polar molecule.
Even with the numbers.
Right. Even though we have polar bonds, right? We do have polar bonds. Maybe write that in here. We have polar bonds. They cancel out, and that results in a non-polar molecule, right? We're looking for, is there uneven distribution of electrons within the full molecule when we're looking at molecular polarity, right? Is there uneven distribution of electrons within the full molecule? And in this case, there's not, right? There's an oxygen on each side. It's really symmetrical. That means things are usually non-polar if they're symmetrical, okay? If you go back to the previous slide with hydrogen with water, maybe write on that one that you have polar bonds, right? We've got polar bonds that create a polar molecule. Okay, so here we do have polar bonds. They show us where the region is. So this is a full-on polar molecule. Oops, can't spell. Right, so there is a chance that you have polar bonds, non-polar molecule, if it all cancels out. Right, it's really about like symmetry within the molecule. If there's not symmetry, it's more likely to be it's more likely to be polar, and if there is symmetry, it's more likely to be non-polar. Okay, last couple things, this is kind of transitioning into looking a little bit more at covalent bonds, okay? And what happens in between electrons in a covalent bond? Are they traded or are they shared? They're shared. Good. Okay. This in a covalent bond, sorry, we're kind of transitioning from 8.3 to 8.4 in your chapters, but we're looking at different things in covalent bonds and covalent molecules, okay? This is talking about when two nonmetals react and form a covalent bond, they share electrons in a way that completes the valence electron configurations of both atoms. Okay, they share electrons in a way that completes the electron configurations for both atoms. So what that means is that when we're looking at carbon, for example, carbon contributes 4 valence electrons. Do you remember our valence electron trends? Group 1 has 1 valence electron. Group 2 has 2 valence electrons. Boron's group is 3. It has 3 valence electrons. Carbon's group is 4. Do you remember all those trends we had with valence electrons? Yes or no?
No.
Okay, it goes by group number. Group 1 is hydrogen. All of them have 1 valence electron. Group 2 has 2. Over to boron is 3. They all have 3. Carbon's 4. Nitrogen's 5. It goes all the way to 8. Okay, the noble gases all have 8 valence electrons. So when they bond, carbon has 4 valence electrons here. Those are the blue ones. Hydrogen gives 1 valence electron each. And by them sharing these and forming a bond...
Doesn't it just make it balanced?
Well, it makes it balanced in that each of them gets to count those electrons as their own.
Yeah.
Right? So now carbon doesn't have just 4 valence electrons anymore. And now with these, it has 8, which is what it wants. It wants a full shell. And hydrogen can only have 2 electrons because it only has an s orbital. Right? So it can only have 2 electrons at all. Okay? We're going to get more into Lewis structures and looking at covalent bonds here in just a second. But this is a little overview with covalent bonds. The next slide is a little overview with ionic bonds. Okay? So we can kind of remember what they do. What's happening? This is now a little review with ionic bonding. When a nonmetal and a metal react to form a compound, the ions form so that the valence electron configuration of the nonmetal achieves the electron configuration of the next noble gas. So that's like a lot of words to say. The nonmetal accepts enough electrons to have a full shell. Right? That's essentially what that's saying. The nonmetal achieves the electron configuration of the next noble gas. Okay, it's really important that we remember that in ionic compounds we have a give and take of electrons. All right, so based on that give and take of electrons and the resulting charges that come from that, we have what are called isoelectronic series, right? Which sounds intense, but it's not at all. All it is a series of atoms or a series of ions and atoms that contain the same number of electrons. That's it. Okay? So this list given to you up here is an isoelectronic series. Okay? Oxygen -2, how many electrons does it have? Oxygen usually has 8. What's the -2 charge tell us?
6.
No, we add 2 electrons to it, so it's got 10. Fluorine usually has 9. It has a -1 charge. So how many electrons does it have? 10. Neon is neutral there. It has 10. Sodium +1. Sodium usually has 11. If it's got a +1 charge, how many electrons does that mean it has? 10, right? Do you see what I'm saying? All of these things are considered isoelectronic because they have the same number of electrons. Right? No matter the proton configuration or no matter, their different element types, they are considered isoelectronic because the number of electrons that they have are the same. Okay? So on the next slide, I want you to come up with you get to pick any alkaline metal, alkaline earth, a noble gas, and a halogen so that they contain the same number of electrons. You're going to come up with an isoelectronic series.
Oh, gosh.
Okay? What's the electron configuration for each species? Determine the number of electrons for each species and the number of protons for each species. Okay, so you're going to pick an alkali metal, group 1, alkaline earth, group 2, halogen, group 7, and noble gas, group 8. Right? You're going to pick 4 different things that have the same number of electrons. Okay, then you're going to write the electron configuration, number of electrons, and number of protons. When it says each species, you're talking about each of your 4 things. Okay, so I'm going to give you about 6 or 7 minutes, maybe less than that, to finish this one.